So in this lesson, we want to look at percent composition and calculating empirical and molecular formula. So now that we know the relationship between mole and mass, we want to show you an application of how finding the moles, also looking at a percent composition of a compound, can help us find empirical formula or molecular formula of any compound. So one important aspect of chemistry and synthesis is characterization of your compound. So whenever you do a synthesis, you always have to characterize it to see what you actually have or confirm that you have the material that you were after. One of the first things that you want to do is finding the empirical formula of the material that you have just synthesized. So we want to show you first how we can find percent compositions, and from there, by using percent compositions and the concept of mole, we will show you how you can find empirical formula and then molecular formula of any given compound. So when we look at a percent composition, we're basically looking at mass percent of each element in a compound. So what is a mass percent of each element? That's the mass of each element divided by molar mass of the compound. So mass percent in general is mass part over the total mass. Now, if you're looking at a mass percent of a known compound with a known chemical formula, you look at the mass of each element over the molar mass of the compound. Now, let's look at a couple of examples, and then I show you if we don't know what the when we don't know what the actual formula is, I show you how we can find the empirical or molecular formula based on the experimental data. But let's do a couple of examples. We first start by known chemical formulas, and then we look at the experimental data. So in general, in order to find the percent composition for a formula that is known, you find the molar mass of the compound, and then you divide the total mass of each element by the compound's molar mass in order to find the percent composition of each element in a compound which is known, where you know what the formula is. So let's look at an example. Let's say you want to find the percent composition of potassium sulfide. Percent composition meaning that you want to find the percent composition of potassium and also percent composition of sulfur in potassium sulfide. So in order to find the percent composition, first of all, we have to find the compound's molar mass, which is the mass of 2 potassium and 1 sulfur atoms, and the molar mass is 110.3 grams per mole. Now, in order to find the percent composition of potassium, that would be the mass of potassium. So in the formula of potassium sulfide, you have 2 potassium atoms. So that would be 2 times 39.10 divided by 110.3. So 70.90% potassium. And the rest is going to be sulfur. Now, a couple of things to keep in mind and remember while we're looking at percent compositions. So if you notice here, potassium sulfide is composed of potassium and sulfur. So once you find the percent composition of potassium and sulfur, the sum of the percent composition of potassium and sulfur should add up to 100%, because potassium sulfide is composed of only potassium and sulfur. That also means that we don't necessarily have to have the mass of every single element in our compound. We could always keep in mind that the mass of the sum of percent composition should add up to 100%. So if you have the percent composition of potassium, you could just from here do 100 minus 79.90, and that would give you 29.1% sulfur. So this is just another way of finding the percent composition of the other element in your compound. So let's look at an example. You want to find the percent composition of oxygen in hydrogen peroxide, H2O2. So percent composition of oxygen is the mass of oxygen in this molecule. So we have 2 oxygen atoms. Each oxygen is 16 grams divided by molar mass of H2O2. So H2O2 is composed of 2 hydrogens plus 2 oxygens times 100. Now percent composition of oxygen in this compound is 94.07%. So let's look at another example. So you have a sample. When you heat this in air, 1.63 grams of zinc reacts with 0.40 grams of oxygen to give zinc oxide. You want to calculate the percent composition of the compound that's formed. Now here, this is how you want to approach this. Zinc oxide is composed of zinc and oxygen. And remember the law of conservation of mass. If you add up 1.63 grams of zinc and react that with 0.40 grams of oxygen, you should end up with exactly 2.03 grams of zinc oxide. So the total mass of your compound is 2.03 grams. Now to find the percent composition of zinc, that's the mass of zinc, which is 1.63 grams, over the total mass, which is 2.03 grams, which is 80.3% of zinc. Now percent composition of oxygen, that would be the mass of oxygen, which is 0.40 grams, divided by the total mass, which is 2.03 grams times 100. That gives you 20% oxygen. Now to double check and make sure we did this correctly, the percent composition of zinc and oxygen, if you add them up together, it should come up to 100%. So since these are experimental, there may be a little bit of an deviation here. So plus or minus 0.5 is still acceptable because these are experimental. Let's look at another example. Aluminum chloride forms by reaction of 13.43 grams of aluminum with 53.18 grams of chlorine. You want to know the percent composition of chlorine in this compound. So remember that percent composition of chlorine is the mass of chlorine divided by total mass, which is the mass of aluminum chloride, times 100. So we have 53.18 grams chlorine, and total mass is the mass of aluminum plus mass of chlorine times 100. Therefore, the percent composition of chlorine is 79.8%. Let's look at a couple of applications of percent compositions and moles. One of the ways that we use these percent compositions and number of moles is to find the empirical formula of compound. Now, empirical formula is the smallest whole ratio of atoms in a compound whereas molecular formula is the actual formula of a compound. So molecular formula represents the total number of atoms in one formula unit of a compound, whereas empirical formula just shows the smallest whole ratio of the atoms. For example, acetylene, C2H2, and benzene. These are two different compounds with two different physical and chemical properties. Now, these are the molecular formula. C2H2 is the molecular formula of acetylene. C6H6 is the molecular formula of benzene. Now, the empirical formula of these both is CH. So the ratio between carbon and hydrogen is 1:1. Now, if you have two formula units, empirical formula units, you will end up with acetylene, C2H2, and if you have 6 empirical formula units, you end up with benzene, which is C6H6. Now, many compounds, it is possible for them to have the same empirical formula, but their molecular formula is going to be different. Now, based on the percent compositions, experimental data, we're going to learn how to find the empirical formula, which is the smallest whole ratio in between the number of atoms, and then we show you how, based on the empirical formula, we can find the exact molecular formula of any given compound. Now, these are the strategies that we're going to use in order to find the empirical formula. So since empirical formula represents the smallest whole ratio in between the atoms, our goal is to find the number of moles of each element in our compound. So from the percent compositions, we want to find the masses. Once we have the mass, we want to find the number of moles. And once we find the number of moles of each element, we're going to try to find the smallest molar ratio in between the element. Now, once we find the smallest molar ratio in between the atoms, we want to make sure that we end up with whole numbers. So this is where it can get a little tricky. If the smallest whole ratios are not whole numbers, we will need to multiply them by a factor in order to get a whole number. So I'll show you how we do all of this. So let's look at an example. You want to calculate the empirical formula for a compound that contains 11.19% hydrogen and 88.79% oxygen. Now remember, the first step is finding the mass, because our eventual goal is finding the number of moles and the smallest molar ratio. So in order to find moles, we have to have the mass. So first step to find empirical formula is finding the actual masses based on the percent compositions. Now, when it says 11.19% hydrogen, we can just assume that we have 100 grams of material. So if you have 100 grams of compound, in that 100 gram, 11.19 gram is hydrogen, the rest of it is oxygen. And it doesn't matter if you have 100 grams, 50 grams, or 25 grams, because percent composition is a ratio, all right? We just assume 100 grams of a sample just to make it easier. So in 100 grams of sample, 11.19 gram is hydrogen and 88.79 gram is oxygen. So based on the percent compositions, I found the mass of each element in this compound. Now, step 2, you want to find the number of moles for each one of these elements. Remember, in order to find the number of moles, you have to use the molar masses. So each mole hydrogen is 1.008 grams of hydrogen, which gives me 11.10 moles of hydrogen. Each mole oxygen is 16 grams of oxygen, which gives us 5.549 moles of oxygen. So step 1, I just found the masses of hydrogen and oxygen. Step 2, I found the number of moles of hydrogen and oxygen. I also want you to pay attention to the fact that I'm not looking at significant figures, rounding, or anything, right? We don't want to round when we find empirical and molecular formulas until towards the very end. If you round in between the steps, your answer is going to be very off. So always keep at least like 3-4 decimal places. Now, I have the number of moles of hydrogen and oxygen. Next step is finding the smallest molar ratio in between hydrogen and oxygen. So finding the smallest molar ratio, sometimes it's very easy. You look at it and you can tell what the ratio is. But the general rule when you can tell easily what the ratio is that you wanna divide the number of moles of every single element by the smallest number of moles you see. So here, number of moles of hydrogen is 11.10. For oxygen, you have 5.549 moles. So obviously 5.549 is smaller than 11.10. So I'm going to divide both of these by 5.549 mole. And by doing that, oxygen becomes 1 and hydrogen becomes 2. And this, I believe, is 1.00. So let's write the decimals too. So this is 1.000 oxygen, and this is 2.00 hydrogen. Now here, the smallest molar ratio that we end up with are whole numbers. So this tells me that the empirical formula of this compound is 1 oxygen and 2 hydrogens. So empirical formula is H2O, 2 hydrogens and 1 oxygen. All right, so let's look at another example. You want to calculate the empirical formula of a compound that contains 56.68% potassium, 8.68% carbon, and 34.73% oxygen. So the first step, let's do it all together. From the percent compositions, you want to find the masses. So 56.68% means you have 56.68 grams potassium. 8.68% carbon, we're going to assume that we have 8.68 grams carbon. And 34.73% oxygen, we're going to assume that we have 34.73 grams of oxygen. Now, second step, we're going to convert this to number of moles. So each mole potassium is 39.10 grams of potassium. which gives us 1.447 moles potassium. Each mole carbon is 12.01 grams of carbon, which gives us 0.723 moles of carbon. And then each mole oxygen is 16 grams of oxygen, which gives us 2.171 moles of oxygen. Now, next step is finding the smallest molar ratio. So the smallest number of moles that I see here is 0.723 moles of carbon. So I'm going to divide everything by 0.723 moles. So that gives us 1 for carbon, 2 for potassium, and then 3 for oxygen. So since we ended up with whole numbers, we can conclude that the empirical formula of this compound is K2, 2 potassium, 1 carbon, and 3 oxygen. So let's do another example. You want to calculate the empirical formula for a compound that contains 2.233 grams of iron and 1.926 grams of sulfur. So step 1, we're gonna find, the masses are already given to us, in fact. So we can go ahead and find the number of moles. So 2.233 grams of iron. And we know that each mole iron is 55.85 grams of iron, which gives us 0.03998 moles of iron. Now for sulfur, we have 1.926 grams of sulfur, and each mole sulfur is 32.07 grams of sulfur, which gives us 0.06006 moles of sulfur. Now, next step is finding the smallest molar ratio in between these two. So to find the smallest molar ratio in between the two, I'm going to divide this by the smallest number of moles. Now, this gives 1 for iron, but for sulfur, it gives 1.502. Now, for iron, we're good because we have a whole number. However, for sulfur, 1.5 is too off. So if you're 0.1 or 0.2 over or under, you can round either up or down. But from 0.3, it's too much. So now we're 0.5 off. Now, what we want to do from here, because our goal is to end up with the whole numbers, the smallest whole number ratio. So we're going to have to multiply this number of moles we found here by a factor in order to end up with the smallest whole number. So how do we find that factor? The best thing is by starting from 1, 2, 3, multiply them and see if you come up with a whole number or not. So obviously, if I multiply both of these by 1, they're not going to change. But if I multiply this by 2, now this becomes 3, and this becomes 2. Now we have a whole number. So therefore, the empirical formula of this compound is 2 irons and 3 sulfur. Just keep in mind that when you multiply by a factor to get a whole number, first of all, it has to be the smallest factor, and then every single element needs to be multiplied by that factor. So now let's see how we can find the molecular formula. So from percent composition, moles, molar ratio, we were able to find the empirical formula. Now our goal is to find the molecular formula. So molecular formula would tell us exactly how many empirical formula units we have in our compound. So the way we can go from empirical formula to a molecular formula is basically by using the molar masses. So the molar mass of any compound is basically the molar mass of the empirical formula unit times number of empirical formula units. So let me show you how we can find this. Our goal is to find the number of empirical formula units. And the way we're going to do that is by dividing the molar mass of your compound, which will be given to you, by the empirical formula mass. That will give us the number of empirical formula units. And then if you have the empirical formula units, you can find the molecular formula. So this N is calculated from this formula. So molar mass divided the empirical formula mass. So let's look at a couple of examples here. As I said, empirical formula times number of empirical formula units gives you the molecular formula. So here is an example. You have a compound with the empirical formula NH2. The molar mass of this compound is given, which is 32.05 grams. You want to find the molecular formula. So empirical formula is given to you. Molar mass is also given to you. You want to find the molecular formula. So in order to find the molecular formula, remember that molecular formula is empirical formula times N. So in order to find the molecular formula, we need to have our empirical formula units basically, so N. So in order to find N, that's the molar mass, which is given to you, 32.05 divided by empirical formula mass. Now, your empirical formula is NH2. So this is the mass of 1 nitrogen and 2 hydrogens. And I get that from the empirical formula because empirical formula is NH2, 1 nitrogen and 2 hydrogens. So from here, N is 2. So your molecular formula is N2H4. So let's look at another example. A compound with the empirical formula of NO2 was found to have a molar mass of 92.00 gram. You want to find the empirical formula for this compound. So remember that empirical formula times N gives you the molecular formula. So in order to find the molecular formula, you need to find N. N is the molar mass, which is 92 grams, divided by empirical formula mass, which is the mass of one nitrogen, plus 2 oxygens. So this gives us 2. So it means that for this compound, we have 2 units of NO2. Therefore, the molecular formula is going to be N2O4. And that's the answer you have to box. So let's look at another example. Propylene contains 14.3% hydrogen and 85.7% carbon and has a molar mass of 42.08 grams. You want to find the molecular formula. So now we put everything together. In order to find the molecular formula, you'll need to find the empirical formula first. So find empirical formula first. And then you want to find the molecular formula. So from percent compositions, you want to find the masses, moles, smallest number of moles, empirical formula. And once you find the empirical formula, you want to find the molecular formula. So let's start by the masses. So 14. So 14.3 grams hydrogen and 85.7 grams carbon. Now to convert to moles, each mole hydrogen is 1.008 grams of hydrogen and each mole carbon is 12.01 grams of carbon. So 14.3 divided by 1.008 is 14.2 moles of hydrogen, and this is 7.14 moles of carbon. Now next step is finding the smallest molar ratio in between these two. So I'm going to divide this by 7.14 mole. So that gives you 1. And this comes out as 1.99, which we can still round it off to 2. So the empirical formula is going to be CH2. Now, to find the molecular formula, we have to find N. So N is going to be the molar mass divided by empirical formula mass, which is the mass of one carbon, plus 2 hydrogens, which comes out as 3. So your molecular formula contains 3 formula units, empirical formula units. So the molecular formula is C3H6.